Dear students, in this lecture we are going to discuss Euler's equation of fluid motion. And this is basically applicable for both liquid and gases. For deriving Euler's equation for fluid motion, we will have to consider three basic ideas. Okay, we will consider in short we are going to consider an ideal liquid, so ideal fluid. So first thing that we are going to consider is that the fluid is steady and streamlined. Okay, so by saying that, what does it mean? That if a liquid is flowing like this, so every molecule of a liquid is having the velocity, all of them are having the same velocity. Okay, so this particular liquid molecule will follow the velocity taken by this molecule. Okay, so and that means the velocity will always be uniform. So you can consider a uniform velocity like say small v. Okay, next thing that we are going to consider is that it is non-viscous liquid. Okay, or fluid. Non-viscous means, as I already discussed in my earlier lecture, that viscosity a kind of frictional force carried by the liquids, okay, while flowing. Okay, so this non-viscous means it doesn't have any kind of frictional force acting between the liquid layers. Okay, viscosity is totally equal to 0. Okay, and it means that the density, and another one is that it is incompressible flow. Okay, incompressible, third condition, the liquid is incompressible, means its bulk modulus will be infinity. Okay, and the density of the liquid is going to be constant. So these are the things that we are going to consider. Now let us start with the derivation. So for that, first of all, let us consider suppose that there is a liquid flowing like this. Okay, and this is the means ground floor or ground level. Okay, this is basically for considering the height of the liquid. Okay, and the liquid is flowing like this. Fine. And what we are going to consider, we will consider a small element of the liquid flow. The liquid is flowing like this. Okay, it may be a tube, it may be any kind of container, a particular pipe through which it is flowing. So I'm just considering this is just a direction of the liquid flow. Okay, and I'm considering a small element of this liquid flow, and it will be like this. Okay, a simple one, say from here to here. And I'm drawing it little bit big because so that when we will consider the geometry, it is easier for you to consider. But otherwise, don't think that is this much big. It's not. That is very small element. Okay, and I will consider that this is of length ds. Okay, and I will consider this is a point A, suppose, and this is a point B. So this is a point A, this is a point B. Okay, and suppose that the pressure, liquid is flowing from here to here, means there must be a pressure difference, isn't it? Otherwise it will not flow. So suppose that this is a pressure P. Since it has flown up to this, their pressure must be greater here. So suppose that pressure is changing with respect to distance. So here suppose that pressure is del P del S ds. Okay, this is a change in pressure. Okay, and this whole liquid element, suppose that it has a mass m, so definitely it will have a weight, isn't it? So the weight is obviously mg. And suppose that let me draw a tangent here like this. Okay, so if this is an angle theta, this weight has two components, all of you know that. So it will be mg sine theta, and this will be mg cos theta. Are you all right with this? Okay, and consider this particular element has a area of cross section of d. It is a cylindrical element we are considering, so it has an area of cross section, means this particular face. Okay, this particular face has an this shaded face has an area of d. All right. Okay, So, and this is B, and what I'm going to consider, so this is at height, say Z2, and this is A. Suppose that this is at a height Z1. So what I will consider, that the distance, this gap, okay, this is called dz, that is nothing but Z2 minus Z1. All right, so this note I have already provided, okay, so you can check for it and then you can go through this particular derivation. Now since the liquid is flowing from here to here, so there must be some resultant force acting on the liquid, isn't it, this element? So if I want to write resultant force on this liquid element, okay, so for resultant force, what we will need to do, force, we have pressure only. See, this is P plus del P plus del S ds, and you know that force is nothing but pressure into area. Okay, here what is the area? It is dA, isn't it? So what is the change in pressure? It goes from P and then it rises up to dP. So initial pressure is P into dA, final pressure is P del P del S ds into dA, okay, and again you can see that this force mg, this has two components, mg sin theta, along with the liquid flow the component is mg cos theta, and this mg cos theta is not helping in the liquid flow, it is in the downward direction, so it is minus mg cos theta, okay. Therefore, if you do this PdA, this will be PdA, isn't it? So they will be cancelled. The only thing remaining is del P del S ds dA minus mg cos theta. Okay. Now another thing that I want to talk about is this is m, isn't it? So mass is nothing but volume into density. Now this particular cylinder has a volume of dA into ds, isn't it? Distance into the area, length of the tube into the area of cross section. So this is nothing but volume, okay. So ds dA, this is a volume, and density is nothing but rho. Fine. So ultimately what happens, I will replace this m by ds dA into rho. So del P del S ds dA minus ds dA rho g cos theta. Alright, so this is a resultant force acting on this particular liquid element. But you know that, but we have a resultant force. Force, what is the formula force for force? Mass into acceleration, isn't it? Okay. Mass is again what? ds dA rho, ds dA rho. Acceleration I will call it as as. Okay. Now to get acceleration, what we need to do, I will tell you that see, we can write acceleration as is equal to dv dt, rate of change of velocity with respect to time, okay. But you know that in this case velocity is again dependent on what? Here we will have to write here, but here velocity is a function of, okay, distance and time. It's well known. So what will happen, dv dt, while writing we will have to do partial differentiation and we will have to write like this, okay, del v del s del t plus del v del t. But since it is a steady flow, this part is going to be 0. Okay, so it will be del V, del S, del S, del T. Del S, del T is nothing but equal to V. Okay, V equal to, so this thing is nothing but velocity. Distance divided by time is velocity. Rate of change of distance, sorry, this thing is nothing but again I'm repeating, acceleration A is equal to dv dt. Dv dt is equal to, since velocity is a function of both distance and time, I'm differentiating is del v del s del t plus del v del t. Del v del t, since we have already considered is a steady flow, del v del t will be equal to 0. So del v del s del t. Del s del t, this rate of change of distance with respect to time, that is nothing but velocity. Okay, and remains del v del s. So del v del s. So ultimately what we have got, as is nothing but v into del v del s. So now we have got as also. So what I am going to write here, ds dA rho v into del v del s. What we have got last, that resultant force is equal to mass into acceleration. Okay, so mass is ds dA into rho. All right, and it is written as as, but we have just obtained that this is ds dA rho. As is nothing but v into dv ds, that we have obtained last, isn't it? Now resultant force, that also we obtained. If you continue from the last note, you can see that it is nothing but dp ds dA minus rho ds dA g cos theta, that thing we will obtain last. So you can see that again I am writing this thing just to make a comparison. ds dA g cos theta. So you can see that here we have ds dA, everywhere it is common. So ds dA gone, here also ds dA gone. So what remains here, it is dp ds minus rho g cos theta equal to rho v dv ds. So can we take all the things on one side? So it will be again dp ds plus rho g cos theta plus rho v dv ds equal to 0. Now one thing we can do is that I can divide this whole thing divided by a rho. So it will be dp ds plus g cos theta plus v dv ds equal to 0. We have cos theta. Now we need to get rid of this cos theta. Okay, so for that let us go back to that particular diagram that we have already drawn. So this is ds and this is theta. You know that this angle is theta. So if I draw something like this, okay, if I do something like this, so this angle is also theta, isn't it? So is it looking like a triangle? So if I consider it A, this is B. If I consider this to be C, then it is like A, B and C. And this thing is nothing but ds. Alright. And you remember this is Z2, this is Z1. So the gap is it around dz. So this thing is dz. And what is this angle? Theta. Okay, so this is obviously 90 degree. So from this what we get? Cos theta is nothing but b by h, means base by hypotenuse. Okay, what is the base here? It is dz. Okay, and what is the hypotenuse? It is ds. So it will be dz by ds. Okay, so can we put this value here? Yes, definitely we can use. So d rho dp ds z dz, sorry, dz ds plus v dv ds equal to 0. So you can see that ds everywhere it is common. So by generalizing I can write 1 by rho dp plus g dz plus v dv. Okay, so this is called the common Euler's equation. Okay, equation for, this is for fluid flow. Okay, I'm not writing liquid flow, it is for fluid flow. Okay, we can specifically do it for a particular flow of a liquid. Okay, for that what we need to do, that we can integrate both the sides. Fine, so how to integrate? For this, let me do this. So what is the basic Euler's equation? That is 1 by rho dp, 1 by rho dp, then g into dz plus v dv equal to 0. This is a general Euler's equation. Now let us integrate it. Integrating both sides. Okay, so 1 by rho is always constant, density of a liquid is always constant. Integration dp, let me know it as p1 to p2, no problem. Okay, similarly g means acceleration due to gravity, so it is going from z1 to z2 and dz. Okay, and then it is integration v dv v1 to v2 and equal to 0. Okay, now what remains? So 1 by rho. Okay, so it is p2 minus p1 plus g z2 minus z1 plus v d means integration x dx. What is that? X square by 2. So here also we have half v square. So what is the lower limit? v1, v2 equal to 0. So half rho p2 minus p1 plus z z2 minus z1 plus half v2 square minus half v1 square. Okay, so can we do one thing? Can we bring p2 by rho, then g z2, then half v2 square in one side, and this is minus p1 by rho. So if it goes on this side, it will be plus p1 by rho, then it is minus gz1. So if I do it, then it will minus, then it goes on this side, it will be plus gz1, then it is minus half v square. If it goes on this side, it will be plus half v1 square. So what remains? Okay, so you can see that this is nothing but a pressure energy, this is nothing but this is z is nothing but height. Okay, this is the potential energy and this is the kinetic energy. Okay, so it is kinetic energy per unit mass, potential energy per unit mass, and it is the pressure energy per unit mass. So it remains constant for one condition and it is also a remaining condition for the another condition. So ultimately, so by summarizing, what we can write, p by rho gz plus half v equal to what? Constant. That means kinetic energy, potential energy, kinetic energy per unit mass, potential energy per unit mass, sorry, this is for kinetic energy, this is for potential energy, and then pressure energy per unit mass is equal to what? Constant. Similarly, if you remember kinetic energy, potential energy plus pressure energy is always what? Constant. Okay, So what does it say? That for an steady, streamlined, incompressible, non-viscous liquid flowing from one point to another point, the total energy always remains constant. That means the sum of kinetic energy, potential energy and pressure energy always remains constant. I am again repeating that for a steady and streamlined flow of a non-viscous and incompressible fluid flowing from one point to another point, the total energy, that means sum of kinetic energy, potential energy and pressure energy always remains constant. So this is known as Bernoulli's theorem. Okay, the statement is given in the note that I have already provided, and there is another alternative derivation for Bernoulli's theorem. So this is a kind of Bernoulli's theorem which you can derive from Euler's equation. So in exam you may be asked to derive Euler's equation, so you can do up to this only, no need to go beyond that. But if you are asked to derive Bernoulli's theorem, you may derive like this also, and there is another way of deriving, so that you can look into the note that I have already provided. If you have any doubt regarding that alternative way, then you can raise question, you can send me messages, and out of these two methods you can choose any one. Okay, it's up to you, whichever you find convenient.